This is question number 1 from the topic of entropy, and it has two parts. The first part says 1 kg of water at 273 Kelvin is brought into contact with a heat reservoir at 373 Kelvin. When water has reached 373 Kelvin, find the entropy change of the water, of the heat reservoir, and of the universe. And the second part of the question is, it says, if water is heated from 273 Kelvin to 373 Kelvin by first bringing it in contact with the reservoir at 323 and then with the reservoir at 373, what will be the entropy change of the universe now? So let's start by solving the first part of the question. And let us pay our attention to this diagram over here. Now what are we doing in this case? Let's write down solution over here. So water is being heated through a finite temperature difference. Okay, so we have heating via a finite temperature difference. Okay, so the entropy of the water, okay, would increase because you have some heat which is coming into this system, which is the system of water. It will be a reservoir which is storing the water, so the entropy of the water will increase. And the entropy of the reservoir, now this is the reservoir through which heat is being taken, okay, so the entropy of the reservoir would decrease. Okay, so I will write down the entropy of water, this would increase, alright, and the entropy of the reservoir, this would decrease. Now the net entropy change of the system, and the system over here is water, this would be a definite positive value. Okay, and the water which is being heated, it is being heated irreversibly. But to find the entropy change of water, we have to assume a reversible path between the end states. So the equation would become delta S system, that is your water, okay, this is equal to integral dq upon t, which is equal to, the end states are between t1, okay, so t1 to t2. Now if you read the question, t1, it starts at 273 Kelvin and it is heated till 373 Kelvin, and this becomes mc dt upon t. So this eventually becomes mc log t2 by t1, which is nothing but mc log 373 by 273. Now if you put in the values of m and c, the value of m is 1 kg and the value of c for water is 4.18. So this will become 1 into 4.18 into natural log of 373 by 273. So you can take out your scientific calculus and do the magic with it. So the value would come about to be 1.305 kilojoule per Kelvin. Okay, now the reservoir temperature, it remains constant irrespective of the amount of heat that is withdrawn from it, because it is of infinite heat capacity. Okay, so the amount of heat absorbed by the system from the reservoir, so let's find that out. So the amount of heat absorbed by the system, now system is always that of the water, so if you go back to the question just for a moment, we have found out the entropy change of the water, that is of the system. Now we have to find out the entropy change of the heat reservoir. So let us find this value, that is the amount of heat absorbed by the system, okay, from the reservoir, alright. Now this is equal to how much, which is mc delta T, isn't it? So mc into delta T, so this would be equal to 1 into 4.18 into 373 minus 273. So if you find this value, it will be somewhere about 418 kilojoules. So this is the amount of heat that is taken from the reservoir by the system, because it increases the temperature from 273 to 373. Okay, so now let's find out the entropy change of the reservoir. Now heat is flowing out of the reservoir, so the entropy would decrease, so it will be a negative change. So entropy change for the reservoir, and this is equal to minus Q upon T. Now how much heat is being taken out? This much heat. So it becomes minus 418 upon the temperature of this is 373, because we just talked about it being a reservoir of infinite capacity, so the temperature would not go down. Okay, so this will be equal to minus 1.122 kilojoule per kg. So this is the entropy change of the reservoir. So what is the next part of this question? That is, we need to find the entropy change of the universe. Now the universe consists of the system and the reservoir. Okay, because this reservoir would be, I think, or we would take it to be the surroundings of the system. Alright, so the delta S of universe, this is equal to delta S of system plus delta S of surroundings. So this would be equal to 1.305 minus 1.122, and this would be equal to 0.183 kilojoule per kg. So this is the change in entropy of the universe. Okay, so with this we have found out all the three parts of the first part of the question, that is the entropy of the system, the entropy change of the reservoir, and the entropy change of the universe. Now let's go to the second part of this question, which says, if water is heated from 273 to 373 by first bringing it in contact with the reservoir at 323 and then with the reservoir at 373, what will be the entropy change of the universe in this situation? Okay, so now this very simple case, not a very difficult case. Now let's go to solution B. Now in this, the water is being heated in two stages. The first stage is from 273 to 323, and then from 323 to 373. Okay, so this is stage 1 and this is stage 2. Alright, so if you have to find out the entropy change of the water, that is the system, this will be equal to, in two stages, this is T1, this is T2, and this is T3. So T1 to T2, and then from T2 to T3. So you'll have T1 to T2 mc dt by T plus integral T2 to T3 mc dt upon T. Isn't it simple as that? So let's put in the values. So you will have, you can take mc to be common, so you'll have 4.18 into 1 and log of 323 by 273 plus log of 373 by 323, and when you put in the values in your scientific calculus, this comes about to be same as before, which is 1.305 kilojoule per Kelvin. Okay, now because we have to find out the entropy change of the universe, so if you write down this equation again, that is the entropy change of universe, now it has a somewhat different equation as compared to the earlier one, but on the same lines. You have a system which is your water, isn't it? So H2O is your system, plus you will have two surroundings. The first surrounding is reservoir 1, and then you will have reservoir 2. So this will sum up the entropy change of the system. So if you go back to the previous part of the same question, now you will have to find out the heat absorbed by the system from the both reservoirs. So we will first of all find out, for reservoir 1 and then for reservoir 2. And in both cases the entropy would decrease, because in both the reservoirs the heat is being extracted, it is flowing out. Okay, so delta S reservoir 1 would be equal to minus Q1 by T. Isn't it? So T1, I would say, it is minus 1 into 4.18 into 323 minus 273 divided by 323, and this becomes equal to minus 0.647 kilojoule per Kelvin. And similarly delta S reservoir 2, and this would be minus Q2 by T2, and this will be minus 1 into 4.18, isn't it, into 373 minus 323 by 373, and this would be equal to minus 0.56. Okay, so now you can put this value over there, this value in the equation, and this value over here. So delta S universe in section B of this question would be 1.305 minus 0.647 minus 0.56. This will be somewhere about 0.098 kilojoules per Kelvin. So this is the amount of entropy change of the universe, which is the combination of system reservoir 1 and reservoir 2. So this is how we look at this question, which is a question on heating via a finite temperature difference. So now after question number 1, let's go on to question number 2.